last presentation of this morning by Professor Zbigniew Bulinski from the Silesian University of Technology in Poland. He's from the Institute of Thermal Technology, and they have very interesting applications of inverse problems to industrial problems. They are related to thermal engineering. So please, Zbigniew.
Okay, thank you very much. At the beginning, I would like to thank organizers for inviting me here. On contrary to the previous presentations, my presentation will be very application-oriented. So I will be talking about the application of POD and Bayesian framework to estimate flow parameters of the in porous medium. So basically, what is the motivation of this work? According to the European Union regulations, biomass is treated as a renewable source of energy, which might be used directly as a fuel or indirectly through the gasification or pyrolysis to produce syngas, which can be further utilized. According to the European Environment Agency, there is like 235 million of tons of oil equivalent per year of biomass, which can be used in Europe to produce different type of energy. Basically, because of this, engineers and scientists are very interested in biomass utilization, and in order to be able to utilize it smart, we need some mathematical models that describe the problem quite accurately. But the problem is that biomass is very random material, and it is very difficult to find some data on the parameters for which might be useful to build mathematical models of, for example, for the flow through the fixed bed or something like this. So we need another approach, like inverse approach, to detect the parameters of the biomass based on the available measurements. And this is what I would like to present you. Basically, we can say about two approaches for modeling flows through the porous medium. The first one, I would say, I would name it like a direct modeling. It needs detailed information about the geometry of the porous material, which basically is two-phase materials. We have solid matrix and some interconnected pores, which are filled with fluid. And this kind of approach usually needs huge computational cost, but it gives us detailed information about the flow field, about the temperature, and so on. For example, as you can see here, this is a type of porous material which is like a polymer net, and the size of the domains is just 3 by 3 millimeters. And to obtain reasonable results, we need something like 2 million cells to solve the problem. So it's very time-consuming, and in case of random material like biomass, it would be very difficult to apply this. So the second approach is based on the volume averaged flow equations inside the porous material. One of the first such equations is the Darcy law, which actually works well for very low Reynolds numbers, so basically for laminar flow inside the pores. slightly more accurate is for Heimer equations, which you can see here. Some other terms which depends on the inertial forces inside appears in this, but most comprehensive description of the fluid flow through the porous material was given by Xu Cheng and Wafai Kim independently. They derive this equation using formal volume averaging of the flow inside the pores. So we have here something like acceleration of the fluid flow inside the pores. We have the pressure gradient, which is the main driving force of the flow. We have the viscous term here, and this is term which describes the interaction between the solid matrix and the fluid flow inside the porous material. So basically, in most cases, these terms depends on the structure of the porous material. The simplest way is to assume dependency on the porosity and pore diameter. So we would like to retrieve values of these two parameters based on some easily available measurements, like, for example, pressure measurements. So we can imagine that this is a fixed bed of porous material filled with the porous material, and we can measure pressure at a couple of points, or rather couple of sections of this porous material. So basically, because the flow depends on the gradient of pressure, we are talking about the pressure difference between, for example, inlet and the other places inside here. So the unknown vector is just the pore diameter and the porosity of this material, and the measured data are the pressure difference at three sections here. Because the shape of the function is like this, I mean, we can see that there probably will be close connection between these parameters. We try to use the statistical inverse formulation. So all unknown quantities are treated as a random variables, as well as the input data. The knowledge on the realization of this quantity is given in the form of the probability distribution. And finally, the solution is also given as a probability distribution of the unknown parameters. So we start with the Bayesian formula. So this is the guy that we are looking for, the a posteriori distribution of the unknown parameters, giving the measurements that are carried out. And in this formulation, we can easily introduce some a priori information about the parameters. And this is the likelihood function, which depends on measurements. The value here in the denominator is just the constant value, actually. So we assume that the likelihood is normally distributed around the given solution for given parameters. And usually there are two approaches for modeling prior distribution. Either we can use Gaussian prior, which brings some information about the unknown parameters, or the uniform prior, which simply describe the range that the parameters might vary. We assume that our prior is uniform one, And finally, we would like to integrate this posterior distribution to obtain the moments of this probability distribution functions. Basically, the average. We used Metropolis-Hastings algorithm, as you can see. So we draw candidate from the proposal distribution, then calculate the acceptance factor, and based on this value, we accept or reject the candidate point. And this results in the Markov chain that quite well sample this unknown distribution, probability distribution function of unknown parameters. The proposal distribution was assumed to be a random walk. So basically, we needed to carry out some checks of this, how this parameter influenced the Markov chain. As you can see here, when it has lower values, the chain is not very nice, as well as its values are too high. So finally, we were able to sample this distribution, and as we imagined at the beginning, there is strong interdependence between those two parameters, even though we were able to obtain some results for this. But the problem was the computational time. It was like 3 days of computation to obtain the distribution of the unknown parameters. So we decided to apply some reduced order approach to reduce computational time of the problem. So basically, we used proper orthogonal decomposition and Sirovich image technique to obtain the reduced basis for our problem. So the single snapshot is a type of the discretized response of our model to the input parameters. It might depend on the time as well as the space, and having this snapshot for different input parameters, we form the snapshot matrix. In our case, the single snapshot, because the problem is steady state actually, the single snapshot was the values of the pressure field inside the discretization cells. So the single snapshot looks more or less like this. So it's not a very nice function, but it doesn't matter. The POD should handle this. And the next step is to decompose the snapshot matrix using singular value decomposition. So we decompose this snapshot matrix to the left singular vectors, which resolve the response surface. Simply, we can assume that this depends on the space and time. In this specific case, just the space. And the product of these two matrices, this is the singular values matrix, and this is the right-hand side matrix of the singular vectors. And we can say that this product actually describes the input space, so how the parameter influences the solution. So this can be seen as something like a variable separation. We have part which belongs on the independent parameter, on the independent variable space and time, and the part which depends on the input parameters. In our case, these are the parameters of the porous material. So what was a little bit surprising for us that when we draw the singular values for this problem, it appears that actually just the first 10 modes resolve the problem. So we were able to truncate the basis up to this 10 or maybe slightly more modes, and that was quite enough to resolve the whole field. But the problem itself is nonlinear from the point of view of the parameters of the porous materials. So basically, we assume that this amplitude matrix is a linear combination of some basis functions. In this case, we use the radial basis functions, the inverse multiquadrics, thin plate spline, or the Gaussian, or the multiquadrics as well. So in such a way, we obtain a POD-RBF network which approximate our pressure field. We check just for curiosity how the number of snapshot influence the solution. So whatever the number of snapshot is, actually this 10 modes is just enough to describe the problem. What was quite interesting, it appears that the approximation error increased with the number of snapshots. This is probably because of the utilization of these radial basis functions, which simply, in this case, in solution of this interpolation problem, results in full matrices, which conditioning decreases with the size quite quickly. So this influences the quality of the approximation. So basically, it is good idea to not to produce too many snapshots, at least in this case, to obtain quite nice approximation. Further, we checked which of the RBFs works the best, and actually it appears that the inverse multiquadrics were the best among all these four. So finally we obtained with the reduced model, and you can see that this reduced model quite well approximate at least in this point the pressure field. Further, we checked how it works in some other points. So randomly we choose some number of samples and calculate the approximation error at each point, and it appears that the approximation error might at some point might be quite significant. So in such a case, the utilization of this reduced model in the inverse analysis might fail simply. But in such a situation, we can use the approximation error model, which is capable to introduce the modeling error inside the inverse procedure. So we slightly modified the likelihood distribution function. We put in here the difference between the reduced model and the exact model, which is simply the approximation error. Further, we assume for simplicity that this approximation error is normally distributed. So finally, it ends up with the nice equation for the likelihood, where we could introduce the approximation error as well as we modified the covariance matrix to take care about the approximation error as well. The prior distribution we left as it was at the at just the pure Markov Monte Carlo approach. And finally, we were able to sample the posteriori distribution. You can see that the error bounds for the parameters are higher than in case of just pure Monte Carlo, but it is obvious because we add some error inside this probability function. But the main idea or the main advantage of this approach is that the computational time decreased to like 5 minutes. So using this approach, we are able to effectively find the unknown parameters of the porous material. And at this moment, we are at the stage to applying this approach for real data gathered on this small gasification unit, as you can see here. So we have the pressure sensor up here, also the temperature sensors. We are able to control the flow through this porous material, and hopefully it will work well for this specific problem. Thank you very much for your attention, and thank you for the cooperation.